Okay, so azeotrope point Y and X Y and X has the same composition. I mean, the vapor liquid has the same composition, so we couldn't separate. So now it's how we learn to separate this composition. If you take a look, we have three pressure plotted at XY, the same composition at 50 kilopascal, 101, and 278. As you saw in my previous Excel plotting, if I change the temperature, the plot changing, composition, everything changes quite significantly. Here the same. So if you take a look at 50 kilopascal, what's the composition? What's the azeotrope point XA equals to? It's on the plot. Yes, 0.743. That means about 74.3% of A. And 1 minus that, XA is the composition of the component B. Does that make sense? And then if you look at 1 kilopascal, what's the composition? Yes, 0.704. And then 278, the composition become 0.641, right? So the composition is changing. So that means if we change the pressure, if we have two columns, we start to change the pressure, we should be able to separate. You will see that how that works in a bit. So first, let's look at, for example, 101 at this plot. On the second plot, if you from the top, it's 1, 2, 3, 4. Okay, so here, this is the azeotrope point. What we can do is like, for example, we have a fade. Let's say we have a fade at 0.4. This is our fade point. Okay, so if we have a fade, and then we can go super close to 0.704, because if you look at here, we have 0.64 here. If we get slightly above this point at this pressure, maybe we can change the pressure there. So how about let's target 0. Let's say 6. Let's say we get super close to this azeotropic point. For example, 0.66 is our target for separation at this point. We have a fade at XA equals 0.4. We want to, at the first column, get about 0.66. And then at the bottom, we want to try to get close to 0.0. So probably we want to get very close to 0.0. I mean, or 0.0, 0.01. It's usually. So what we can do, for example, the first one, we can just start to craft the columns. For example, we can just go, you learned this before, right? In the last class. So we can just go to construct the first column at 101 kilopascal. We can do this part of separation, put into the stages to separate it. So you can just go and go, keep moving. And then keep getting up a little bit more here. So actually, if you keep drawing here, going down here, you can get at the bottom, you can get almost to 0.0%, I mean 0.0% molar frac ratio of acetone. Basically at here, acetonitrile, at here you can get XA almost equals to 0.01 or 0.0. Does that make sense? Does that make sense?
So we don't use the 0.7 or the
Here, because at this point, we would never be able to separate anything, because if you, so we want to get slightly below this point and get to achieve our first step of separation. So basically we have a fade at 0.4, and then at this first stage, we just do this to get close to that point. For example, our target is 0.66. You can go 0.7, but that's very close to 0.704. So you want to avoid that slightly lower. And then here, if we don't look at there, so basically, if we look at the like below this azeotrope point, we will be able at the one end get almost pure component B. Does that make sense? And at the top, we got 0.66 at 101 kilopascal. So now the magic become, how about we add a second column at 268 with this top product from the first column as fade. So here, this point is 0.641. And then what's the composition we got from the top of this first column? 0.66 as a fade to this column. So for example, our fade become here. Did we bypass the arrow short point? Does that make sense? Basically, we have for example, if we have think about if we have two columns, one operate at 101 kilopascal. We do separation, we got almost pure B at the bottom, and we, at the top we have 0.46466 as a composition A, XA. Does that make sense to you? Look at the plot. We put 0.4 input, and we do the run at the first column. We got bottom, it's almost pure B, and top we got 0.66 right below this arrow choke point. That makes sense? And then we're so smart. What we are going to do? We're going to bring this first product at the top to the second column as a fade at 278. So that fade become here. Make sense? We fade to the second column. So then what we're going to do? We can just add trace to, for example, we want to achieve almost 100% A at the top. We just add trace to do the equilibrium. I didn't draw. This should be parallel, but I did a bad job. I'm just trying to demonstrate you. And then you can go all the way, add trace, and then you can almost get to the point very close to, for example, 0.99 XA, like that. Does that make sense? So our fade is 0.66, and then the top product, if you read, is very close to 100% acetone nitrile, 0.99. We just bypass that azeotrope point. Does that make sense to you? Theoretically, take a moment to think.
So the feed stream from the first graph, the 0.4, that's just, we can choose whatever feed we want.
Yeah. I'm just demonstrating you. But you don't want to choose fade at 0.704 because you will never be able to fade to separate at that pressure.
So you want to choose something that's just a little bit off.
Yeah, you want to choose something below and then later have a second, you want to choose a point, fade point composition below this at this pressure. And then once that you will look at that, you will look at maybe you want to choose a ladder like operating pressure. Have that, make sure your top product is above, composition is above this aerotrope composition. Does that make sense? So if we put in plot, it will look like this because we are looking at the acetone nitrile and water. So the first low pressure column, that's our 101 kilopascal. Our fade, for example, XA equals 0.4. And then our bottom is almost 99 point, let's say 99 point water, almost pure water. You can get almost close to 100% water. So what's the top coming out? 0.66, right? That's our first lower pressure column. And then we transfer this to, this is just tell you that like the azeotrope is 0.704 from here, but ignore that. So you go all the way past here, you have 0.66 composition of the mixture coming into this column. After you pass through all the stages, at the end, you can almost get very close to 1.0, like 100% acetonitrile, probably less than that. Does that make sense? This is our 278 kilopascal column. So this is called what's called a pressure swing distillation column. You just alter the pressure to change these points and then get separate. So at one column, you almost get 100% acetonitrile, the other is get water. That make any sense to you?
So how do you know when to like trace it up or trace it?
What do you mean?
Like see on the left, move it down, on the right, and on the graph.
Oh, this?
The X, Y.
Two graphs on the bottom.
So here, X and Y. Why I put X, Y here? It's because usually you will go through at the top part, usually it's actually Y. But why I put X there? It's because you usually will have, in the real situation, you will have a condenser to condense that vapor composition to become a liquid. So you can kind of, sometimes at the top, where's my marker? Let me find my marker. Oh, here. So basically, in your distillation column, for example, you have this coming out. You have your fade coming in. Again, this probably also help you review. So here, usually on top, it's vapor and YA composition, but to collect the product. So here you will have a condenser. What happens when the vapor goes through a condenser? Become liquid at the top, and then XA at the top. These are the same composition. And the bottom, you will have a liquid product, and with XA. Don't confuse this XA and this XA. They're different. Because here, why I call it XA, because this is the vapor and with composition of YA condensed to liquid. Does that make sense? Do we understand what's going on there? Take a minute to think about. Or it's very confusing. Oh, no.